Hi, hello everyone, and welcome to my topic, animation QE based on dependency graph. My name is Viachaslau. I am team lead at Glera Games. And our project, where we use this animation QE, is Riddle Road. Riddle Road is a solitaire game where you should explore some events, explore some story, and play in the solitaire at the same time. So we mainly play the solitaire game, and we should ensure that players have a looking good solitaire with good dynamic, with smooth animation, and so on. So to ensure this, we tried several approaches. The best of them turned out to be an animation QE with dependency graph. So let's imagine that each of you is a designer, game designer, and a programmer at the same time, and you should make a solitaire or similar game, but we'll speak about the solitaire. In order to do this, we need to implement the basic entities of the game. First of them is game logic. So we have structure about card. It has ID, type, suit, so on. We have game state, which is just a collection of cards, board, stock, and waste. Just as mentioned, all my samples will be will use pseudocode, but it's just a sample. So it can be on C++ or C# and so on, even on Go.Engine, because this is just a concept, not a real code. So we create these components, and we create a game logic. Game logic is an entity which contains game state, has two events to indicate that something changed, and has some methods which allow to interact with game logic. For example, one real method is turn play board card, which is pretty simple. It moves card to waste from board, makes board stable, and check if game ends or not. Pretty simple. During movement, we emit a signal about our card moved to waste. Which benefits we have now? Our game logic works synchronously. It has no dependencies on other components. It knows nothing about who will use its events. And all their actions perform in one update at the same time. So no waiting, no asynchronous callbacks. And we need something which can handle all events from game logic. So we add basic components. First of them is animation, which is a simple class that can be executed. And animation can contain any logic not really using animations. Because, for example, in Riddle Road, we use spine animation. But here, we can use any game engine possibilities, any third-party possibilities. And because, for example, we use Cocos engine and spine animations, so our animation can be create spine, set some tracks, move it to the new position, then run another tracks, and so on. So here can be anything you want. And we should implement handler that subscribes on game logic events and then creates animations and executes them. Just connect and run. Pretty simple. Let's see what we achieved. Can you start? So it works. We play a card, we open underlying cards, everything okay. But this is simple Solitaire. So then a game designer comes to us and says, everything is OK, but we should add more mechanics to our Solitaire, because just playing cards is not enough. And we decide to add 2 more mechanics. First of them is a plus card. Plus card is a spawner, which adds more cards to our stock when we open it on the board. No need to play it. And the second one is a half cards, because everyone loves match 3, so we have 2 half cards that merge into 1 real card when we open both of them. Sounds good. Let's implement them. So we have a working mechanism, so just extend them. We add 2 more events, and we add 2 more checks. Now we check closed cards, we check if we need emerge cards, and we check if we need an activate plus cards. And our stabilization becomes recursive, because during some actions we can trigger other events, so we need to recheck them until the board will be stable. And emit 2 signals. And in our handler, we just connect new signals with new events with new methods where we create new animations and execute them. OK, so let's see what's happened. Can you start? Can you start them? Chaos. It doesn't work. Our last solution doesn't work. So we need to fix them, because everything runs in the same at the same time, and we need to fix this. So the first idea that comes to mind, we should run animations not at the same time when they come to handler, but one by one. To ensure this, we should implement animation queue, and our animation changes. It receives an event, so we can know when this animation ends. And a queue, which has 2 main methods. First of them, add animation to the queue, and the second one tries to start a first animation from queue. Now our queue pretty simple. It checks if we have now animation in progress. If yes, so we stop. If no, we execute first awaiting animation from our key. OK, and animation handler now not executes animation, but plays them in our queue. Pretty simple. Let's check what we have. Looks better than it was. But we can improve this. How we do this? The second idea, we can run animations with dependencies. So this is the name of dependency graph from the beginning. We can think of animation as a command operation that requires some objects to be free to start. These objects we call resources. So animation will have a list of 2 resources. Which of them should be free for animation to start. And the second one is the resources which animation blocks during its execution. So, for example, if 2 animations depend on the same resource, the first one begins to execute and blocks this resource. So the second one can be started before the first animation completes. These resources can be any object string into another animation. We use strings, for example, because it's easy to debug. So we have now 2 lists, and our animation tree becomes more completed. First, we check which resource is blocked now. We check all running animations and add to blocked resources list all its blocks. Then, for each awaiting animation, we check. Can we start them or not? We can start them if none of the required resources is blocked. If we can start, we start it. If no, we just add the resources to the blocked to prevent other animations depending on this awaiting to start. And remove all complete animations from our key. So let's check. This is even better, because now we have 2 animations in parallel. All of this speed ups our gameplay. But this is, so this is the graph. Blue ones is required resources. Yellow ones is blocked resource. And blue-yellow is blocked and required at the same time. So our first animation required waste resource and card 0 resource. This is the source of this card. And it blocks all underlying cards. 1 and 2. So when the first animation completes, it releases all its resources. So possible for animation number 2 to start. It also blocks animation number 3 to start, because it captures resource stock, and it prevents animation open closed, because it captures resource card 3 and card 1. So when it's finished, it becomes possible for animation number 3 and open closed to execute, and so on. So once again, can you start it? So once again, play, activate plus, then open and play second one card. This example from our animation resources. This is from real project. So you can see there are many animation resources. Not the whole bunch of them, but you can make resource on any entity or any component you want. This list can be infinite, in fact. And this is how we enable these dependencies. So for example, we mark them this way. So you can see this animation requires many resources and blocks many resources at the same time. But we can do this even better. For example, no need to hold all resources until the very end. We can release some of them during execution. For example, when our plus animation becomes to actuate, there is a moment when Can you start it? There is a moment when sorry. When there's two moments. When first of them, when the plus card enters the center of the board, and the second part when the cards from centered card fly to the stock. So when our plus cards entered center, we can release resources of the underlying cards. To make our dynamic better. So we add another event about resource releasing to our animation and subscribe on them in animation queue. And let's check. So as you can see, we speed up our dynamic a little, but this is the whole talk that I want to speak to you. It's not so big, but this is the working solution that we use in our Solitaire. It works just fine for us. Just by configuring these dependencies. These dependencies can be configured by game designer, by the programmer, by someone who wants to do it. And it's very flexible mechanism due to its nature. You can release resources at any time to enable fine interactions of our mechanics, because there are only 3 of them, but we have about 15 maybe, even more. So without this mechanism, we will have only chaos. So that's all.
Okay, thank you very much.
If you have